All right, so for our final activity for this round of taking a look at things in light, we're going to do experiment 10 or activity 10, polarization. And what we're going to do is we're going to set this thing up as it says here. Rather than using the crossed arrow target, which has an opening to allow us to see the ball, because I'm using my cell phone camera, it's really, really sensitive and it sees a lot of light. So instead what I've done is I've taken the viewing screen, and simply, as you can see, I've taken the viewing screen and I've just placed it over the light to get a nice bright, sort of a bright veil over the light, so I don't keep on blinding my phone. And what we're going to do is we're going to take a device. It's not a diffraction grating. It's called a polarizer or polarization filter, as you can see here. This is a PASCO polarizer or polarization filter, and it has a compass on it, 0 at the top, 180 on the bottom. And very much like the diffraction grating, it doesn't have slits, little tiny slits, but it does have vertical lines, and the vertical lines allow the light, again, if we view it as waves, if I get the chance to do the dolphin swim again, up and down, vertical light goes up and down like my finger here. So the light is going through up and down at that 0 degree mark, if I can do this. But light that's going side to side, like my finger here, it gets blocked because it has to be in the same orientation as one of these slits. So just like the slit plate before that had 7 slits, this has, hundreds of thousands of slits. It's not a diffraction grating. It's not meant to be a diffraction grating, but it has hundreds of thousands of little tiny slits that the vertical light can just fit through. It's sort of like doing this. So maybe another analogy is this. If I were to take this particular piece of paper and do it this way, this is vertical, and I were to have a mail slot that was vertical, it would fit through this way, but if I turned it, it wouldn't fit this way. It wouldn't fit sideways. So usually a mail slot is horizontal in a door. So mail will fit through sideways, but it won't fit up and down. So this is what we mean by the polarization of light. The light is, if it was a sine wave that was written on this piece of paper going up and down, this is vertical polarization. I need to be flat, obviously. This is horizontal polarization, and this is 45-degree polarization. So what we're going to do to play with that is we're going to take this polarizer, and if I spin it and let me go ahead and turn off my little tiny lamp over here. There we go. So there's our light again. And if I take our polarizer and look at our light and I spin it, you'll notice that there isn't much going on. You really can't tell that I'm spinning it, even though I am. It doesn't seem to change what's going on because the light coming out of our light box down there, which is made by the random collisions of our electrons, which causes them to randomly accelerate in all kinds of directions, means that we have light that is random in its polarization. Not that it goes from 90 and then it randomly jumps to 27 and then it randomly jumps to 185. It just means that all of those photons contain a jumble of polarizations. So what I'm going to do is I'm going to turn on the light again. Sorry, phone. Here we go. Turn on the light. Excellent. I'm going to take my little polarizer and I'm going to go ahead and put it in this polarization holder here and get it to snap in. Come on, you can do it. There we go. And this holder has a notch on top, and it allows me to arrange this to be vertically polarized. So there we go. Nice. So 0 at the top, or darn close to it. Right, there we go. And I can put it on the optics bench, and I can look at our light, look at our little screen down there. Turn this off. So now I can't see it from the front, but again, here we go again. There we go. It is 0 at the top, 180 at the bottom, 90 to the right, 270 to the left. And now I'm taking a look at it. But what I'm going to do is I'm going to take an identical polarizer next to it, this guy. And what I'm going to do is I'm going to take it is also up and down. So if I already have light that is vertically polarized like my hand, and it's already flying through this filter, that means that horizontally polarized light is getting blocked, much like the red light was blocked by the green filter. This is blocking all light that is not vertically up and down. This is a vertical polarizer, or it's a polarizer set to vertical, and so is this. So what happens is, how we show this, is I'm going to take the second vertical polarizer and do this in the dark, and place it down here. And now I'm going to look on it, and so there's the light. You can see all the fingerprints. I can't really tell that I put a second polarizer in front of it, because maybe it's a little bit brighter because it's another piece of plastic. But yeah, my phone's doing a pretty good job of showing it. Okay, so the way this works, the way that we discovered polarization, who's we, the scientists discovered polarization, is if I take this second polarizer and I go ahead and spin it, come on, you can do it, spin it to 90 degrees. Now I'm going to try to do this without using my phone. I'm going to put my phone down. Sorry guys, we're going dark. We are dark as I spin this because it takes 2 hands. This is a 2-hand experiment. It's not a 1-hand experiment. Fantastic. What I have done, we're back. I've taken this second polarizer and I put it on its side. So now, if PASCO did a great job of doing this, if I take this guy away, that's the vertical polarizer, and I put the horizontally polarized light, and I go ahead and take a look at this, okay? Again, I still see light going through there. I can take it away. It gets a little bit brighter because it happens to be there. Again, still the same thing. Here is horizontally polarized. Move it over here in the dark. Let's see if we can do this. Grab the other guy. This is the vertical polarizer. Make sure I don't confuse them. This is the vertical. Still there, okay? But of course, what's special about this is if we theoretically imagine that the random light where my finger is back here is in all different directions, this vertically polarized polarizer selects just the vertical. This other guy over here is the side to side. Now what I'm going to do is I'm going to try to do this in the dark. I'm going to go ahead and put this down here, and you'll notice it gets dark. It doesn't disappear. Again, these aren't perfect polarizers, but if I go ahead and move this out of the way, there's the light. Now it's polarized. Well, let me go ahead and remove this out of its filter. It may be that's not perfectly aligned. Let me go ahead and take my hand and just do this. Just for fun, I'm going to go ahead and turn on the light so I can see what's going on. I'm going to grab this second filter over here by 0 up top. There's 0 up top. Wonderful. And I'm going to go ahead and turn this off and do this again, working in the dark. There's our light. There's our vertical polarizer. I'm going to start spinning this polarizer, and you're going to notice that it's going to go dark. In fact, the best I can do is this little purple dude. It is not dark all the way. It's flickering because my hand is moving. I'm going to try to get it steady. So these are crossed polarizers, okay? And what I can do is I can increase the intensity by just spinning this second polarizer, because what I'm doing is I'm blocking or absorbing those photons that are not the correct orientation. This is vertical. It's the same orientation. It appears to be about just as bright. I feel like an eye test. Which is better, number 1 or number 2? And then if I spin it, I can go ahead and make this darker as I go through, which is kind of cool. So by using 2 polarizers and spinning them, I can go ahead and make the light almost disappear. And this is exactly the way that flat screen TVs work. Now, OLEDs, organic light emitting diodes, they actually turn the diodes up and turn them down. But light, the LEDs, and the LCD displays, what they do is they turn the polarizers on and off, and that's what adjusts the brightness by just turning the polarization selection of these guys back and around. Now I'm gonna, after I get done with this, I'm gonna move over to my monitor and see if we can't see that. The other thing I want to do is I want to take a look at the reflection on this screen here. What I'm going to do is I'm in the dark. I'm going to sit up here, and you'll see there's a whole bunch of reflection off of this this piece of metal here. It turns out when the light comes out of this light source and hits, the light that is reflected off of this surface happens to be reflected in a particular orientation. You can't see with my eyes. The horizontal light comes down and bounces and then comes back up to our thing. But the vertical light does not do a very good job of reflecting well. So it turns out that reflection has yet another rule as far as polarization in, polarization out. But it turns out that it's not perfectly angle in equals angle out. It really depends on the orientation of the reflection. I'm going to see if this guy works. So what I can do is I can spin this guy, and especially in here, this center guy right here, you're going to notice that the reflection happens to disappear. Now, so the light is not disappearing, but the reflection is. There the reflection is very bright in the middle, but if I go ahead and turn this, it goes away. That's not a shadow. What I'm doing is I'm blocking the light that is reflecting off of that center strip. You can see I'm getting a different reflection by the magnet strip on the side. And what that does is that it might be the same thing. Yeah, there you go. Look at the light coming off of, oh, it went away. There he is, back. We're back again. Am I blocking the light? Let me see if I can do this right. I'm going to go ahead and put this guy in front of my lens here. And I'm going to see if I can, yeah, there we go. So I don't want to block this. So there's the light coming off of the wood grain of this little box I'm working on. If I go ahead and I spin this, it turns out I should be able to make some of that reflection go away. Now, the problem is my phone keeps on re-upping the intensity. It keeps on changing it, but you can see that it is dimming out and dimming back in. And this is why especially baseball players like to wear polarized lenses, because it keeps the glare off of the grass, off of the field. The same thing happens with wearing polarized lenses when you are when you're driving, or especially when you're boating on the water. You can get a glare off of the surface of the water. If you happen to wear lenses that happen to be vertically polarized as opposed to horizontally polarized, it'll block some of that glare out, which is kind of cool. So I'm going to stop this, and I'm going to head over to my monitors, and I'm going to see if I can see any difference when I go ahead and use my displays, my flat screens. I think I have a 23-inch over there, and I use this polarizer to go in front of the light to see if it does the same thing with my polarized light, because this is the technology that allows my monitor, at 60 frames per second, or 120 or 240, depending on what type of monitor you have, allows us to see different images. So I'm going to turn this off and see what happens.